We're pleased to have with us today Dr. Michael Waite. Dr. Waite is an associate research scientist in the Department of Mechanical Engineering at Columbia University. His research focuses on the transition to a low carbon energy system, especially with respect to interrelated effects of building energy systems, variable renewable energy, and local energy distribution systems. His dissertation research analyzed regional energy infrastructure with emphasis on wind power, building heating, and distributed generation. Before we welcome Dr. Waite, I just want to let you know that at the end of his presentation, we will ask for questions. You will be able to ask your questions live using the blue hand raise in Zoom. So once we ask for questions, if you have a question, you can raise your hand in Zoom. Ashley will give you permission to talk, and then you can ask your question live. So with that, please join me, at least virtually, in welcoming Dr. Waite.
Thank you, Professor Ray. Can everyone hear me? Can you hear me?
I can hear you, yeah.
Thanks for having me virtually. It's a pleasure to be able to speak with everyone at Dartmouth about my research. Let me just make sure I can see everything clearly. I tried to sort of lay this out in a way that kind of cover the core important aspects of the research that I'm hoping can spur some discussion, and then I've got some additional topics I can cover depending on the time, but I'm hoping even in the Zoom environment we can have a healthy discussion in the Q&A time. So in general, what I'm going to talk about is the transition to reducing greenhouse gas emissions from buildings generally, and the focus of the talk is really going to be on heating systems and how that integrates with what's happening on the renewable energy side. And so just to give an overview, I'm going to talk about both kind of current trends and related to the energy and emissions context, a vision for what a transition will look like, and this is going to be a mix of sort of trends and data as well as some work that I've done. Then I'm going to present a new building heating model and how that lets us assess pathways to decarbonize, reduce the carbon emissions from heating systems and buildings. Then we'll use some regional energy analyses to look at, specifically what happens when we build out supply in a different way, primarily renewable energy, and when we do things on the end use demand side. I'm going to be primarily focused on electrification of heating, so the conversion of fossil fuels to electricity-based systems. And this will look kind of rosy, but there are challenges to doing this type of heating decarbonization, not purely the scale. And I'll use that to talk about a potential transitional approach. And then the last bullet point here, implications and opportunities for buildings in this context. The degree to which we talk about that will kind of depend on time, but I hope to touch on some things. So the current context. This is just showing the kind of trends from 1990 to 2018 of where our energy related greenhouse gas emissions come from in the United States. For a long time, electricity was the bulk of it. That's dropped primarily because of a switch from coal to gas, and we'll talk about that in a bit. And buildings are down kind of at 11% here, but often what happens in these types of accounting is the electricity in the building sector gets separated, and really it's something like 3/4 of the electric energy goes to buildings. So that really puts us on par with the leading causes, which is transportation primarily. So you can think of transportation and buildings as pretty similar. And the vast majority of these emissions, I realize that probably a lot of people know some of this context, so bear with me. The vast majority of these emissions come from burning fossil fuels. So that's burning fossil fuels in buildings for heat primarily, also hot water and cooking, and burning fossil fuels to generate electricity, and burning them to run vehicles and for industrial processes. So methane leakage is important, working to quantify that. There's other sources, but primarily burning fossil fuels. So given that, given that buildings use a lot of energy and produce a lot of emissions, how much of that is for space heating? And across the US, most of the work I'm showing is at this point is across the US, but I'm going to touch on sort of the combination of New England and New York, which is where you are, where I'm from, and where I live and work now. So about, more than half of residential building emissions in the US can be attributed to space heating. And if we go to, the cold region that we live in and the Northeast, that gets up to like 70% of the greenhouse gas emissions. Mostly this is going to look higher than what if you're familiar with any of these numbers, this looks higher because through processes we've been using, found that most greenhouse gas inventories tend to underestimate the emissions from electric heating, underestimate the effects of methane leakage, so the space heating impacts tends to be bigger. Highly dependent on where you are in the country, so it depends on a number of things, including the thermal efficiency of your building and your equipment, but what drives the overall effects are climate, whether you're in a cold region, what type of heating fuel you use, and the regional electricity supply mix. So the current space heating landscape in the US is what's shown here. And this is a result of some analysis we've done that I'll get into later. But essentially, much of the US uses either natural gas, that's about half of the heating energy, or electricity, that's about a third of the residential heated area in the country. But because there's a lot of potential for still coal-based electricity generation, the emissions from electricity can be significant. Now that tends to be in warmer regions where electricity is located. So if we look at sort of the broader US context, more than 2/3 of the heating energy is from fossil fuels, almost 60% of heating related emissions. But if we're talking about the Northeast region that we're in, both heating energy and emissions creeps up to starting to approach 90% of the heating loads here. And this is just zooming in on that picture. Here in the northeastern US, we also use a lot more fuel oil. So there's two primary systems: natural gas, which comes through a grid and tends to be concentrated in denser areas, urban areas, and fuel oil, which tends to be in more rural areas, but is also in these kind of older cities that we have in the Northeast. But I want to focus primarily in this talk on fossil fuels being the main concern when it comes to heating, because these cannot be widely replaced by low or no carbon fuels on site. So it really starts to look at a situation where we need to convert those fossil fuel-based systems to electricity-based systems, but we also need to make sure that we're driving down the use of fossil fuels in the electricity sector. It's generally seen as the approach we should be taking. But as I said, so this plot shows the emissions rate for a unit of electricity delivered for different regions of the United States. The one on the left is the average or total emissions rate, and for all electricity generated, and on the right, it's the non-baseload emissions rate. So why this is important is that baseload electricity, what comes every day, there might be kind of daily patterns in energy use, but there's a reliable plug-in equipment, lighting, and these types of things that come every day. That's generally considered the base load of a region. And then things like cooling and heating, which are temperature dependent and seasonal, tend to be served by non-base load generators. The challenge is that the vast majority of the current low carbon electricity supply, that's primarily nuclear and hydropower, is base load generation. So when we're looking at decarbonizing heating and cooling to a degree, we have a lot less currently available low carbon resources. So what's happening in the current landscape is how much coal do you have and how do we build out low carbon resources to meet non-base load demands. So let's look at what's going on in the electricity kind of sector in the US right now. Major trends: coal is essentially has cut in half in the past decade or so in terms of the electricity generated by coal. The amount of electricity generated from natural gas is essentially doubled, so that's largely the replacement there. But there has been growth in what I'm saying are low carbon resources. A low carbon resource is renewable energy, wind, solar, and hydropower, as well as nuclear power. The majority of the low carbon electricity currently still comes from nuclear power. That's the yellow line in the plot on the right, and hydropower, which is this kind of maroon line. But the growth has all been in wind and solar power. We tapped our hydro resources long ago, and we're not building any new nuclear power in this country. Not really. There's a couple potential ones coming online. One important point I want to make about this growth in renewables, and what I want to use the term regularly is variable renewable energy, because the supply from wind and solar is variable, not fixed. So one important point is that the majority of this electricity, this capacity, is installed at the utility scale. It's connected to the grid. So, we tend to see a lot of solar panels on rooftops and in parking lots and people's backyards and things like that, but that's a relatively small portion of the amount of renewable energy overall, and even a relatively small portion of the total wind and solar power installed in the US. So at this point, I just want to summarize what I take from these kind of contextual considerations. One is that reducing building emissions will probably require electrification of heating, and coupled with increased renewable energy on the grid. Buildings' share of all end-use energy and emissions are likely to increase as we see more and more electricity go into buildings. And in the future, I haven't touched on this here, but if there's a build out of electric vehicles and more kind of electricity and transportation sector, a lot of that charging is going to be done at home or in parking garages and in buildings. So that's an overall shift as well. I want to kind of assume that most future emissions reductions and low carbon energy supply is going to come from variable renewable energy. I also want to assume that a large part of the energy transition is going to occur through grids, through things like the electricity grid and gas systems, rather than there's a role for distributed resources. I'm going to talk about that later. But fully off-grid operation is probably unlikely for the typical scenario. And what this kind of swirl of grids and building changes and different fuel streams means is that buildings are going to become more complex nodes that require controls to operate optimally in this kind of future integrated energy system. The last one I will hopefully convince you of during the talk. So the first thing we need to get a handle on is, pardon me, we don't really know right now how much energy is being used for thermal loads and when. We can measure electricity very well, and we know at kind of regional level, various zonal levels, how much electricity is being used hourly, sub-hourly even. But when it comes to the thermal loads of a building and fossil fuel usage, we don't really know that. And that's because, we're looking at a situation where wind and solar power is only available when it's windy or sunny. It's highly time dependent, and we need to get a better handle on the time dependence of the thermal loads, heating specifically. So to do that, we recently produced the first high spatial resolution, high time resolution model building thermal load and fossil fuel usage data. We published this, but this data we've also made freely available. So you can contact me if you'd like to figure out how to get it and use it yourselves. The challenge here is that we also want to see what's going on at the distribution level. So I talked about the need for high time resolution, but we also wanted high spatial resolution. So a model we developed, and I can't go into like too many details given the time, but what we end up with using a whole mess of available data sets and various statistical and data science approaches came up with at the census tract level. And you can think of a census tract as on the order of a population of 4,000 people. So, a lot of data is available at the state level, sometimes large city level, like New York City. But to get down to that level, it's pretty rare. So we've established an approach for doing that largely, and current work I'm adapting that to do kind of some more sophisticated planning analyses as well. But for now, I want to focus on what having this temperature dependent residential and commercial building time series allows us to investigate. I want to take a moment to talk about why this is important, and the real reason is because we want to get a handle on what the current fossil fuel usage is, because we want to know what would the new electricity usage look like if we did heating electrification. There's several different ways of doing this. There's several types of heat pumps. The primary one is an air source heat pump, and the heat pump is the same technology as a typical air conditioning system. It simply has a valve that lets it operate in reverse. And the key benefit of this is that because even when it's cold outside, you can extract some amount of heat out of the external environment. You're not at absolute zero. So even if it's cold for us walking outside, there's still some heat there. The benefit of that in using a refrigeration cycle is that we can extract more heat out of that environment than electricity that we put into the compressor. And what this means is if we look at the efficiency, called the coefficient of performance of a heat pump, the coefficient of performance is almost always greater than 1, but it is very dependent on the outside air temperature. So you have a system that can be highly efficient at moderate temperatures and requires a decent amount of electricity at low exterior temperatures. So that dynamic has pretty significant implications for how we do energy system planning going forward. We've computed that, using existing equipment, currently available equipment, not necessarily what's existing in buildings, but currently available equipment, a coefficient performance of greater than 4 average across the US could be achieved, but that really depends on what region you're in, as well as what the temperature is outside. But let's get a handle on what kind of we can accomplish in the current grid with the shift from fossil fuel-based heating to electric heat pumps. And we recently kind of quantified this looking at, what the plots here show is the fraction of the of heat pump emissions versus natural gas in the top left, fuel on the top right, propane in the bottom left, and electric resistance heating. Typically, that's the way that electric heating is done now. It's just a hot wire that produces a drafter that you pass air over. And that's an issue because we still use a lot of fossil fuels to generate that electricity. So we need to see efficiency improvements. Even this estimate is actually something to be somewhat optimistic about. We basically estimate that we can cut in half greenhouse gas emissions from heating using the current grid and using currently available technologies. There are pathways to improve technologies for heat pumps. In terms of overall emissions, we're not going to get much better than where we are now, but there are other reasons to continue working on heat pump technology. I'll talk about those a bit later. And so it's very easy to sort of make a table and make some figures, but in the real world, we need to change, greater than 90% of all heating system capacity just to achieve the numbers that I show on this table. And eventually, what we're looking at is possibly replacing 100% of heating capacity. There are tens of millions of buildings in the United States, and this type of scale of operation and what the policy levers are to make this type of thing happen we don't really have a historical model to point to for that. And buildings last a lot longer than cars and industrial equipment. So if we want to electrify vehicles, that's something as a society we might be able to turn over on 10-year type of timelines. But buildings that last 100 years, we just have to take a different approach. But for now, given that challenge, it's really the only way to drive down heating emissions as the grid cleans, as we incorporate more low carbon electricity on the grid, and as we switch from coal to natural gas. So what I'm showing here is similar map plots to what I showed on the previous page. And what we're looking at is the emissions from heat pumps versus the emissions from burning natural gas in your building. The left column here shows, the current electricity grid fossil fuel mix, which includes a decent amount of coal. And as you go down, we're replacing a certain amount of fossil fuel in electricity generation with renewables or low carbon electricity. So you should be able to see two things. Oh, the right side is, imagine that all coal is eliminated in the electricity grid. And what you can see is, to drive down from this kind of starting point where we are now to deep emissions reductions, we're going to have to see a combination of this electrified heating and probably a shift away from coal, but certainly a shift towards low carbon electricity in place of fossil fuels generally. But one thing I want to talk about is that heat pumps, electric heating, is not the lowest emission option at all times. So this is looking at binary decisions between, do you heat with natural gas or some fossil fuel, or do you heat with electric heat pumps? And the fact is, as I alluded to, what we're talking about is really an existing building challenge, and most of those existing buildings in cold climates have fossil fuel-based heating. So one option we've been looking at quite a bit is, rather than tearing out and replacing that existing fossil fuel system, heating system in a building, if we maintain that when we install new electric heat pumps, and operate them in a way to minimize emissions at all times, that's something where we can allow ourselves flexibility in the larger transition to less carbon intensive energy. Let me show a picture of what I'm talking about. So on the left side, this is just a model building in kind of a, let's say something like the median climate in the United States. On the left side, it's just showing the most important lines here are the red line and the green line. The red line is the gas demand, what the gas demand for heating would be versus temperature. The green line is what the electricity load versus temperature for electric heating would be, electric heat pumps. And because, as I was saying, the emissions rates are different from burning fossil fuels on site or from the electricity that's delivered to a home, there's some temperature below which the emissions from burning fossil fuels, burning natural gas in your building are going to be less than the emissions associated with using the electric heat pump for heating. And in my example here, that's that dashed line. So it would be called the changeover temperature. So when temperatures are below that dashed line, the best choice is to use burning gas in your furnace or boiler, and to the right side, it's using electricity for heating. If you look at just the temperatures, which is the left side, it looks as though that's an awful lot of heating that we'd still be relying on fossil fuels for. But even in fairly cold climates, the extreme temperatures are pretty infrequent. So on the right side, what I'm showing here is scaling that temperature by the actual average hours in a year it occurs. And you can see that that dashed line shifts quite a bit farther to the left. So, even though heat pumps are higher emissions at low temperatures are infrequent. So the amount of heating energy that can be provided by heat pumps is significantly larger than it might look if you're just looking at the left-hand figure here. Oh, and another benefit is that it allows smaller heat pumps to be used. So there are a lot of challenges around, centrifugal equipment like compressors generally being operated at part load. It's also very expensive to size a heating system for, the full load of a building versus part of that load. So there are benefits to kind of this transitional approach in terms of cost and thermal comfort as well. This just mirrors the figures I was showing before, but instead of looking at only heat pump only systems, we're looking at heat pumps in dual source systems. That's what we're calling a heating system that has both heat pumps and natural gas or other fossil fuel heating. The main takeaway I want you to gather from this is, still as we go down, we're increasing the amount of low carbon electricity in the grid. And on the right side, what you can see is the amount of heating energy, the percentage of heating energy that comes from electricity, where in this very faint yellow is 100%. And you can see in cold areas of the upper Midwest that rely a lot on coal, at first, a decent amount in the existing grid, a decent amount of that heating is going to still be done by fossil fuels, but it doesn't take much kind of cleaning of the grid to start to see a shift to using more electricity. And that electricity is going to be at lower and lower emissions rates. I want to get too much. One thing we've done with this is started charting pathways to deep greenhouse gas emissions reductions. On the left side is just various pathways that look at historical growth rates of renewable energy, historical growth rates of heat pumps to get at, what might be needed to get at very deep greenhouse gas emissions reductions. In general, we think of a target of at least 80% emissions reductions by 2050 as our kind of benchmark for reducing greenhouse gas emissions to mitigate the worst effects of climate change. And to do this, this is just a general charting across the US. It looks as though we need to more than double or at least double the rate of growth of renewable energy and have a much more accelerated adoption of electric heat pumps than we're seeing right now. So that's the kind of broad strokes of what needs to be done looking across the US. But of course, once we get into different regions, different states, we start to, run into additional complexities. So one thing is the diversity of heating fuels, which I already talked about. But then there are things like the availability of resources. Where are good wind and solar resources? Where is there already existing hydropower? What are the transmission constraints, and what do the local distribution systems look like? So we can get a handle on sort of the direction we should be going, but we really need to start looking at regional systems in order to solve these problems. I want to focus first on wind power and heating, because it tends to be that the wind resource is better where it's colder, better than the solar resource. That makes sense. It's farther north. So here's just one quick plot of if we're looking at multiple years of data and we want to get a handle on the seasonal demand versus seasonal potential supply, the red here shows a range of monthly electricity demands. This is for New York State, and I'm going to go into more detail on that system in a bit. But you can see that even in a northern climate, we still currently have a cooling-driven summer peak electricity demand. What happens with wind, which is the best resource we really have available to us here, is that we have the opposite. It's windier in the potential wind generation in the winter is significantly higher than in the summer. It's about a 2-to-1 difference. So this was one reason why, one of the motivating reasons for looking at what happened, or how we can sort of tackle this general seasonal difference in supply and demand. One thing I'm going to talk about a bit is that the idea of curtailment. So what that is essentially, if you've got wind or solar power potential generation available, but there's no demand for it, then you curtail that potential electricity generation. You don't generate it. And that has primarily economic viability issues for wind and solar, because right now storage is generally too expensive to mitigate this problem. There are benefits to energy storage, but large scale shifts in energy supply is not yet kind of one of the benefits. Yeah. So one point I want to make here is that even though these are monthly kind of averages, the wind power will fluctuate dramatically and significantly more than the demand. I'll talk about that more in a bit. So anyway, this is what motivates us to look at electrifying heating in the context of a system that has more and more wind power. We looked at this region of New York State, and just some important notes about this system. It's fairly complex, but what you can think of it as is there's one kind of large area where there's very good onshore wind power resource, and there's existing hydropower resources. There's kind of this middle region where this is like where Albany is, and areas north of New York City, where there's a lot of transmission capacity. Actually, the major demands are in what I'm saying is region 3, which is New York City and Westchester County suburbs. And then there's kind of this edge region of Long Island that's significant, highly residential, with some potential resources. The one thing that comes up, and I won't talk about this at first, is that off of New York City and Long Island, it's traditionally been seen as not a good area for renewables, but now that offshore wind viability or offshore wind is becoming more viable, we're starting to look at that quite a bit. So to assess this, it's an optimization problem with a lot of variables and a lot of different scenarios we've been looking at. The main thing, let me first focus on, I'm happy to talk after the fact about methods. Maybe I won't go into it too much given time. The main thing I first want to focus on is what's the effect on wind power. Now I want to focus on the capacity factor. So that's essentially the average production from the wind or from any generator divided by its capacity. So, you know, there's some effect of simply, if you look at the black line, there's some effect of you just have better wind resource, higher winds in some areas than in others. So as you install more and more of these resources, you're likely to be seeing it installed at, you know, less and less productive sites. But there's a bunch of other things that can cause curtailment and reduce that capacity factor. So the big curtailment effects in this existing system is simply the misalignment of supply and demand. So that starts to make the capacity factor even lower. Sorry, the x-axis is I'm installing more and more wind capacity. So just the misalignment of supply and demand has significant impact. The fact that we have existing low carbon electricity generation in the system has an impact. So, you know, often there's a focus on wind and solar power, but we certainly don't want to build it out only to displace potential clean electricity generation from hydropower and depending on your views on existing nuclear power. And then there are transmission constraints that can also kind of cause curtailment, reduce our capacity factor. So those are the dominant effects that are going to affect the viability of wind power. And that curtailment, so the red here is the actual model production of wind from the analysis. The blue and the purple are the curtailment. And if you see, you know, that this is January 2007, January 2008, this is all model data, but it's a highly seasonal effect where, you know, under the current kind of electricity demand regime, we would expect a lot of that curtailment to happen during the winter. So that's sort of where we see the benefits of pairing heating electrification and wind power expansion. Now we want to recently, well, this should be coming out soon, a paper, but New York State and other states have fairly ambitious climate policies now, and we wanted to look at, you know, what's the optimal approach to meet these types of targets that are being laid out in policy. So right now, in the state of New York, there are targets for, and these are codified in law, to see 70% of electricity generated from renewables by the year 2030. At the same time, a 40% reduction in greenhouse gas emissions from the baseline. By 2040, and here's where things start to get quite ambitious and a little challenging, 100% of electricity generated from low carbon sources. And then by 2050, major reductions in greenhouse gas emissions from 1990 levels. That's the baseline. So we, in a modified our state regional system model to investigate pathways to deep decarbonization. I'm about to show a pretty complex plot, but I'll describe what it's showing. So we ran a bunch of scenarios with different percentages of low carbon electricity. That's the shape of the points on the plot. And you can see the legend in the upper left. And then we also ran it with different percentages of heating and transportation converted to electricity, high efficiency heat pumps or electric vehicles. And that's what the color of the points indicates. The y-axis is the levelized cost of electricity. So the levelized cost of electricity incorporates the cost of, you know, capital costs, operational costs, fuel costs, cost of the transmission system, so all these different components. And so we're using that as a benchmark for, well, what's the kind of better prioritization pathway? And what we find is, again, as I said, as the shapes change, we're bringing on more and more low carbon electricity, primarily new renewables. And that's what we see is the kind of cost of electricity really start to blow up as we start to approach the star is 70%. We're still pretty stable, but beyond that, we start to see dramatic increases potentially in the cost of electricity. Whereas if you include, or if we prioritize electrifying these end uses of heating and transportation, then we can maintain lower electricity costs that are more in line with the current electricity costs for much longer. And why this is important to realize is that out here where we're talking about like in the 2040 to 2050 timeline, when we're looking at approaching 100% renewables or low carbon electricity supply, we don't really know right now what that world is going to look like, and what technologies are going to be available or spurred by the overall shift in the economy oriented towards low carbon energy supply. So we're sort of supporting this research sort of supports the idea that we should be prioritizing a pathway that provides us with flexibility later to adapt to those any technology changes. I'm going to skip these numbers for now. But there are challenges to widespread heating electrification. There are challenges to widespread vehicle electrification as well, but I'm focusing on heating now. The primary challenge is that it's a capacity problem. So we have what would accompany this heating electrification is a pretty vast build out of new electricity infrastructure capacity. If you recall, I can't see it here, but as I showed before, that's pretty infrequently used, that new electricity capacity. So it would be very expensive to operate a new infrastructure, hard infrastructure, new grids with low capacity utilization. At the same time, I talked a bit about the capacity of the heat pumps and that they would need to be significantly oversized, and that's a challenge as well. Luckily, the existing fossil fuel distribution system is pretty robust and quite a bit cheaper than the existing or new electricity system. So just looking at why this matters or why this happens, if you just want to consider the heating load variability, this is over a long time frame of about 50 years. The red line is for Baltimore, which is the kind of moderate climate zone in the United States. And you can see not only do we have much higher potential heating loads than cooling driven loads, that's the blue line, but year-to-year fluctuations are huge. So to build new infrastructure dealing with this type of variability is a difficult planning challenge, to say the least. This is, so revisiting the heating model I talked about earlier, this is the kind of current fossil fuel peak to electricity demand peak ratio. Red is, implies lower numbers, warmer climates, and where this presents a challenge is where this number starts to get greater than 2 or 3 or even 4. And if you see that pretty much the entire Northeast, we're talking about the current ability to deliver heat is about 4 times greater than the current ability to deliver electricity. We're dealing with existing systems. We might do things differently if we were starting over with a completely, green field compared to transitioning existing systems. So we want to get a handle on how much heating can be done in the current system and what challenges there are with, moving beyond that. So what I wanted to do is for each census tract in the United States, compute the increase in peak electricity demand with 100% high efficiency electricity heat pumps. This is a proxy for new capacity needs. And then also, what's the maximum heat pump penetration we can achieve at the census tract level without exceeding the current peak demand. So the left this is going to look very similar to the plot I showed before, but this is the computed new peak electricity ratio, or the ratio of the computed new peak electricity with all electric space heating to the current peak electricity demand. And again, you can see that the Northeast is quite a challenge, but the dense urban areas in New York City isn't quite as much of a challenge as the rest of New York State and New England. But what's kind of missing from this is that electricity infrastructure in those dense areas is much more expensive. So the cost of tackling this issue doesn't necessarily look the same as this picture does. Yeah, so overall, we'd be looking at, we're computing about a 70% increase in electricity delivery capacity, but that the capacity factor, the capacity utilization of that new capacity is 1%. So we need to think a bit differently about this, because we're unlikely to nearly double our electricity distribution, transmission, and generation capacity only to use it 1 out of every 100 hours of the year. So what can be achieved in the existing system? And that's what this shows. So the plot on the right is how much the amount of electric heat pump penetration we compute that we could achieve in the existing system constraints. And in warmer areas, it looks pretty good, but much of the country, the cold areas, the Northeast, the Rocky Mountains, the upper Midwest, we're looking at maybe 20% is like Vermont and 35% is New Jersey. So that's about what we're looking at for within the current system constraints. So I want to revisit this idea of dual source systems that I brought up before, because earlier I was talking about doing this for an emissions optimization perspective, but we can also, because the gas demand is much larger than the existing electricity demand, we could also control these to operate to avoid those types of loads that would cause strains on the local electricity system or require new build outs. And so one thing I didn't show before, because it's tough to zoom in on, now I've zoomed in on that plot of the annual fractions of the year, but now I'm only looking at the bottom 6% of the year. And let me move this out of the way. I don't know if that was blocking you, but now we can look at a change over temperature that manages the peak load, prevents our new peak electricity load from exceeding our current peak electricity load. Oops. And this is an even smaller portion of the year than controlling for emissions. One thing I should note is this dotted line here is where you would want to control it for emissions reduction at very with a very clean grid. So there's some point as we build out renewables and as we get rid of coal that we would be hurting emissions by controlling it to just manage the peak load. What I want to stress is that that's a very small portion of the year, and we can quantify what that means. So the overall kind of takeaway, let me give you the overall takeaway from this approach, which is, currently about 70% of US heating is based on fossil fuels. If we install, when I'm saying this maximum heat pump scenario without requiring new build out of underutilized electricity infrastructure, we can reduce the fossil fuel heating to 43%. If we maintain those existing fossil fuel systems, if we don't see it as binary and we consider using these dual source systems, then we can drive the use of fossil fuels for heating down to such a small amount that it's on the order of less than 3% of heating. So we basically are maintaining these systems to to serve the coldest times of the year, but they allow a much deeper penetration overall in terms of the ability to shift away from on-site burning of fossil fuels. This is really just pushing, just supporting the idea of kind of a more integrated and holistic way of thinking, rather than, you know, an either or. We're transitioning on the electricity side. You know, we've got fossil fuels that we're continuously, hopefully we're going to continuously biting into. We should consider the same type of approach on the demand side, where we, you know, ramp down fossil fuels, fuel usage, perhaps, rather than try to eliminate it in 90+% of buildings out, you know, overnight. This is something I'm not going to get into because I want to leave some time for discussion, but there are to kind of realize all the benefits of this approach. My current work is really looking at the control systems needed to realize these benefits. But I also want to say that, you know, kind of the point I was just making, and maybe we'll leave it here, is that this also motivates rethinking the gas system and fossil fuel system. So there's a lot of potential from, you know, alternative fuels. There's a lot of work being done looking at hydrogen. How do we mix that into the gas system? But mostly what I want to kind of leave the thinking with here is that getting out of binary kind of thinking when it comes to these large infrastructure systems, it can be, you know, we have a tendency to do studies that produce very nice, clean numbers and, you know, tables like I showed before. But when we're dealing with existing robust energy systems and infrastructure, it becomes a much more complex challenge. So as one example, and I'll leave it here, you know, storage gets a lot, I've only touched on storage just a little bit and it gets a lot of attention, but where we stand right now is that, you know, the y-axis here is the total US storage capacity right now, and it's a log scale. The total number of this is the total number of batteries in the US right now. This is pumped hydro electricity storage, which is connected, you know, to the grid and really was largely built out with nuclear power. This is if we add up all of the gas tanks in vehicles, on-road vehicles in the US. And this is the last bar here is the total amount of underground natural gas storage in the US. So we have this massive battery. And if we abandon that system without considering, you know, how to utilize this existing capacity, we could be setting ourselves up for, you know, something that looks very good on paper, but is a difficult transition to achieve in the real world. I'm going to skip over what I have there and just kind of leave this open to questions, but I do want to kind of acknowledge my collaborators and you know, funding support from NSF and from internal Columbia funding, as well as we've worked, well, I didn't show this project, but we worked with a manufacturer of water side building heating and cooling equipment on some pretty extensive and interesting research projects as well. So leaving it there, I'll open it up to questions and hopefully some discussion.